4.6, the last section in chapter 4, is optimization. So what we did in 4.5, finding absolute maximums and absolute minimums, was setting us up so that we could take a look at these problems. So these are all applications, they're word problems. I really feel these problems feel a lot like related rates. Very different sorts of problems, but in my mind, I always associated the two. So what we're going to do, we're going to find an absolute max or an absolute min, either one or the other, depending on what the problem asks for, of a function on an interval. Now the difference is we might have to come up with that function and definitely the interval on our own based on the description. Sometimes they give us those things, but usually we have to come up with those, and that's typically the hardest part. Okay, so let's dive in and take a look at one about as simple as they get. Find the maximum area of a rectangle if the perimeter is fixed at 76 feet. The maximum, okay, so we've got a rectangle, maximize the area. We know what the perimeter is going to be. It's almost like we have a fixed amount of materials, let's say, to build that rectangle. We just want to make the area as big as possible. So I would recommend, especially for problems such as this, give yourself a drawing. And it looks like I've already given part of it away. Give yourself a simple rectangle and label the sides. So we've got this length and that length, X and Y. We are looking to maximize the area. Well, what's the area of the rectangle that I just drew? Well, length times width, right? X times Y. Okay. They also mention the perimeter. Well, let's come up with an equation for the perimeter here, but we know that it's going to be 76 feet. Well, there's an X here, there's another X here, there's a Y, there's another Y, right? 2X plus 2Y, the perimeter. 2X plus 2Y, but this time we know what it's going to equal. We're going to use exactly 76 feet of whatever it is that we're building this with. Okay. That second equation where we know what it equals, that's referred to as the constraint. I'm not really going to use that sort of language in the rest of the examples, but if you come across that maybe in the textbook or somewhere else, what is the constraint of this optimization problem? So there's what you want to maximize or minimize. That's more like a typical function. And then there's your constraint. What's your limitations, right? Okay, so here's what we're going to do. You notice that the thing we're trying to maximize, the area, it has two variables. That's not good, right? So if you look back what this is all based on, absolute maxes and mins, we try to maximize or minimize a function with just one variable, x, and it's got an interval. Okay, so we're working towards that. We need our function to only have x, and then we're also going to have to come up with an interval. So how can we, to get things started, how can we rewrite this area formula so that it only has x, not x and y? And the key is we're going to take advantage of that constraint. Here's what we're going to do. Okay, so kind of writing it out again, we need a equals xy in terms of x only. Okay, so we're going to use this. How are we going to do that? What if we were to solve for y and then plug it in? And I'll just kind of reveal this. So pretty quickly we can isolate y. Y will equal 38 minus x. And we're going to take that, 38 minus x, and put it in for y right there. So pretty slick way to take advantage of your constraint so that you can leverage it, if you will, to get your function in terms of one variable. And why don't we go ahead and simplify that? X times 38 minus x, a equals 38x minus x squared. Okay. So now we know what the area will be just in terms of x. Pretty cool. But we still have some work to do before we can go through the process of an absolute max or min. So let me repeat what we have here just to start off a new page. We've got that area formula. But what is the interval? The question now becomes, what's the interval AB of x? What are the smallest value of x and the biggest value of x that x can take? Well, again, we're going to look back at our constraint. If 2x plus 2y equals 76, well, if you simplify that, which you might have even thought of earlier, x plus y equals 38. Think of it in the simplified form. It'll be a little bit easier for us. What is the smallest value that x could take? And what is the biggest or largest value that x could take? Okay, what is the smallest x? What is the largest x? Obviously, y is going to have to fluctuate as x changes. You think, well, the smallest that x could be is 0. If x is 0, y could be 38, and that'll be fine. Okay, so the smallest that x could be is 0. What's the biggest that x could be? Well, maybe once I answer this one seems easier. The biggest that x could take is 38. If x is 38, then y becomes 0. And that constraint is still going to work out just fine. So I've got the smallest value of x and the largest value of x. The interval is 0 to 38. So we're going to try and maximize our area, a equals 38x minus x squared, on the interval 0 to 38. Now, you may be thinking, wait a second. The smallest and the largest. Can we just pause there for a second? Let's look back at that drawing, right? X, y. You're telling me that x could be 0? Technically, yes. If x is 0, then y, then x shrinks down and y, becomes like, it's almost like the rectangle has shrunk down to have 0 area. And you just have like these two sides, that are smushed right up on top of one another. And y becomes 38 and 38, so that the total distance around is still 76. Doesn't make any sense to create an area like that, but you could, in theory, right? Or what if x is 38? So, if we smash it the other way, right? So x is 38, y is 0, so there's no gap this way. So x is 38 and then another 38, so the total distance around the perimeter is 76. Yeah. Now, remember, we're trying to maximize the area. So probably we're not going to want either of these to be true, but we need those boundaries. Certainly x can't be negative, and we can't make x any bigger than 38 because we got to double back, right? Okay. We know it's somewhere between. Well, at this point, now it becomes a problem from 4.5, right? We're going to find the absolute maximum of that function on this interval. So, of course, we need to know all the steps for that. It took a lot of work just to get to here. That's the essence of this section, just getting to this point. Now we got to remember our previous steps. Well, I'll tell you, to maximize your function, first thing you need are the criticals. So we're going to find the derivative. Pretty straightforward in this case. Again, it's pretty common in these applications that getting the formula is by far the hardest part. At that point, the derivatives and things tend to be pretty, immediate, is the tendency. Okay, so we've got the derivative. We're going to set that equal to 0, and we're going to think about when it might not exist. Well, setting it equal to 0, that goes pretty quick. X equals 19. Okay. And when might that derivative not exist? Well, we're never dividing by x, so never. we get the one critical value. Okay. So now if you think back to the procedure for finding an absolute max and min, what you do, you take any critical number and you plug that value of x back in to the original right here. You also take the two endpoints of your interval and plug them in. And those three y values are your candidates for the potential absolute max. So we're going to take 19, plug it in into A. We're going to take 0, we're going to take 38, plug it into A. We're going to find the areas associated with each of those three x values. So I've got that here. And I'm going to go ahead and let's keep A. Actually, that's not A. Oh, man, can I fit it all? All right, let's keep it all on the screen. So 19, haven't done this part yet. 38 times 19 minus 19 squared. I got 361. 361. A equals 0. Well, plugging 0 in is going to be 0. And 38, plugging 38 in. Well, 38 times 38 minus 38 squared. Guess what? That's 0 as well. So we can conclude 361 is the biggest out of those. So that is the absolute max. Really doesn't surprise us that the endpoints produce 0, right? Because we were smashing the rectangle both ways. It's that middle number, that critical, that gave us this absolute max. And at this point, we really want to be clear that we've answered the question that was posed. Here, the question was simply what is the maximum area? Sometimes they change up exactly what they're asking for, so we want to be super clear. What is the maximum area? And we got it. The maximum area is that 361, and in this case, it's feet squared. In other problems, they might not ask for the maximum area itself. They might ask like what dimensions of the rectangle produce the maximum area, because that would be more useful if you were actually going to build it rather than maybe what the area actually is. And well, if you were looking for the dimensions, and we can kind of note that out here, the dimensions of the rectangle, well, we know the x value. X is 19. How would we get the y value? Well, if you recall, I have to go back to my other page. What did we have? Y equals y. Y equals 38 minus x. We had that earlier in the problem. So, well, x is 19, then y is going to be 19 also. Turns out, to produce the maximum area, you actually want to square a 19 by 19 square. So those would be the dimensions. But that gives you the area itself, 361. Okay, let's stop the first video here with this example. I think we're going to do one example per video as they tend to be lengthy. So I'll see you in the next one.